Okay, so what I'm going to do is talk about statistical models from networks from the current slide. Okay, and this is it's a much too big of a problem for the next time that I have to talk about this problem today. So it's going to be a little bit fast, and it's going to be, again, get at the conceptual set to see what's there. We have two ways of thinking about this. One is the graph is the dependent variable, so we're actually trying to explain the graph itself and what predicts the extent of ties and the different ways you might do this. And then the alternative is the graph is the independent variable, so we want to use the network to predict some outcome as we go. And so we'll talk through mainly on the first one, and in fact the vast majority of time is going to be spent on these exponential random graph models once we get there. Now when I say that this is a deep field and we're just barely scratching the surface, the point of course is that the history of random graphs, which is really what all of this work is based on, is a deep mathematical field. So random graph theory and sort of processes on random graphs, it's a well-known series in mathematical and physical sciences and statistical sciences that we're just going to spend a little bit of time on. But you can kind of trace the applied roots, the part of the world that we're going to spend most of our time in here, comes back through a series of ideas. And I want to give you a very informal understanding of what some of these ideas are so that we can get a sense of it. If you want to do more, and some of you will, and I strongly encourage it, check out these books. So there are some great books out there that have gone on over the last 10 years or so that have been building on these sets of models. For those of us in the social sciences, and you really want to sort of dig into statistical modeling of networks, the Inferential Network Statistics Analysis book in 2021 that just came out by Bruce Damaris and his friends and Kramer is an excellent book. Also, we have the basic intro in our textbook, and the handbook has a series of chapters. There's also, the literature on this field has gotten really deep, so there's plenty of work to do it. For those of you that are statistical modelers and formal statisticians, I highly recommend Eric's book. It comes with some R packages that go with it. They're a little depreciated at this point because he hasn't updated them, but it gets you into the nuts and bolts of how this stuff works. So, network inferences problem are a little different than the kind of inference problems that we as social sciences are used to thinking about. So we're used to thinking about the inference problem of I sample a dozen nodes, they tell me some variable like their value, like the mean on those dozen nodes. How likely is it that that number applies to the rest of the population? So we're trying to infer from a sample to the population. In the random graph world, we really want to assume the network we have when we do a network analysis is the population. So there is no inference question, right? So I don't need to infer whether or not this network is representative of the population because I have the population. I've solved that problem by assumption, so I can go home, right? So there's nothing to do. So what are we actually trying to do? What we're trying to do is figure out whether or not this object that we've seen, this network object, would be observed by chance alone or not. So if I were to take this network and flip a coin, would I observe the same thing? So in a counterfactual, Marvel multiverse kind of world, to continue the geek sort of strain we've gone through the last couple of days, would I found the same thing in lots of different sort of versions of the universe, or is the version I had really unique? And so that's the key that we want to go to. And so it turns out that how we get there is a little bit hard to do. The core problem with it, like we see in a lot of things, is combinatorial. The number of possible graphs of the size of any graphs we aim to see grows, I hate the word grows exponentially because the exponent could be, negative, but you get the idea. Geometrically is a better phrase, right? So the number of possible graphs that are out there that you could compare your graph to is really big. And so we can't just go out and actually do a physical comparison to the universe of possible graphs. And so what we need to do is have some kind of a construction feature or some kind of an element that lets us assume what the universe of possible graphs looks like so that we can make sense of it. And the simplest possible universe of graphs we could have is known as an Erdos-Renyi graph. In an Erdos-Renyi graph, for each cell of the adjacency matrix, I flip a coin. Right? The edge is either on or off. And when you do that, the beauty of that process of defining a coin flip process or a random assignment process is that we can know some things that are very constant about the graph. So some really good formal proofs and understanding of what's going to happen. So for example, we know that we're going to end up with a Poisson degree distribution in the network or something like this. We also have some great sort of theory that shows us that when you do that process of flipping a coin, that if the average degree in the network crosses 1 of a pure random rating graph, you go through a phase transition where you have lots of disconnected pieces, a short ramp up, and a fully connected graph. Right? Notice one interesting feature of this. Right? It's not the density of the graph, it's the average degree. So this applies for a network of 100 nodes, 1,000 nodes, 1,000,000 nodes. That's kind of mind-blowing, right? It's kind of amazing that these practices have. But it's all in this assumption that the process that we're dealing with is a purely random coin flip kind of process. So what we'd like to know, of course, is that the simple random graph is a really poor model for real life. So very few of us have formed our relations entirely by random. We have something else going on. And so we need to condition on more than just the coin flip. We need to condition on other features of the graph, like the probability that we'll be in the same room, or we're the same age, or these other kind of features. So we can do that. Now it turns out, excuse me, it turns out that some types of these conditionings, we refer to this narrowing of the set of possible random graphs as conditioning. So some of these conditionings are well known. So we can condition, for example, on the distributions of degree. So we know that if some people send more ties than others, then it's likely that they're going to have more connections than the people who send a few. And so that's an easy thing to condition on. We condition on the ties sent, the ties received. We can condition on groups in the network. So there's lots of things we can do. And oftentimes there's a trade-off between this exact uniform set and sort of a set of algorithms for getting there. So for example, there's a great set of tools that Stan Wasserman came up with in the late 60s and early 70s for calculating the expected number of triads in a network relative to the number of the distribution of dyads in that graph. So if I know the number of asymmetric and mutual ties in the network, then I can calculate the expected number on the probability of seeing one of these kinds of triads, and thus the expected value, and I can compare the observed number to the expected and get some kind of a distance score. And that's great, because that allows us to compare it to an element, the distribution of dyads, that should be controlling the number of triads. And so once I know the distribution of dyads, then I can ask whether there's a preference for the number of triads that's above and beyond what we'd expect by chance. So for example, you might say that the fact that there's only 5 complete triads in this network, and I remember there's a few hundred nodes in this network, I forget how many, but 5 seems like a small number. But 5 is almost 10 times what you'd expect by chance, given the distribution of dyads in this network. And so it's actually, there seems to be a preference for closed triads in this network that you wouldn't have observed by just looking at the count. So that kind of conditioning is the process we're going to do throughout our set. And so this is, we do that process, for example, in the ad health data, and it turns out that across all of our schools, so this is a box plot of these expected values compared to observed values for all of this 200 different schools in ad health. I think it's about the right number, 120 some odd. And so what you find, of course, is that there's a relatively strong preference for transitive ties. So this notion that a friend of a friend is a friend, right? We see those kinds of triads observed more than we would otherwise, and we're unlikely to find these cyclic triads, or particularly these triads where a friend of a friend is not connected at all. And so this has some intuition about what drives the kind of networks we observe in these settings, and we can get those insights by looking at these conditionings. Turns out that if you know the distribution of triads, you also can say something about the global hierarchy in these networks, this is some really fun work that's been shown that if you constrain a network to get rid of particular types of triads, it implies that you must have certain kinds of macrostructures in the network. And just drawing a blank on the author's name for this work. It's like Jimmy, it'll come back to me later in the set. But what's nice is we have indices for these. So we can actually go through each of our schools and say, well, what kind of archetypical clustering system characterizes, in this case, in-grade networks in schools? And what you find is that we tend to have networks that are akin to this kind of hierarchical clustering or this collection of clusters kinds of model. And you might imagine, these models don't tell us how big these cliques are or these components are, but we know that these networks have this kind of clustered hierarchy and often multiple branches. And in these schools, these are sixth graders, what you end up having are usually boys and girls, right? So we know that by looking at these kind of clusters. So that's the advantage of random graphs. I'm not going to spend any more time really on where random net graphs themselves come from, just to say there are models out there for testing known random graphs of different kinds of patterns, different kind of micro constraints on the graph that then that allow you to judge your observed graph against us. We tend to take a much more constructionist approach to this kind of random graph construction. And it's to imagine, instead of saying that if a simple random graph doesn't fit our model, maybe a collection of aggregated simple random graphs would do it. So imagine I give you a network that looks like this. And so this is a network of adolescents. And in this case, there's race mixing. And so we find that the probability density of ties within the white group is higher than the density of the ties from whites to blacks or from whites to others. And if you look across the diagonal, right, that there's more ties on the diagonal than there is off the diagonal. So that's a block structure in this network. And so I know that a pure random graph isn't going to help, but I could construct a graph that is random and meets that. So I could say, let's have a network where I have the probability of I assign nodes as they match the population, and I match the density, but I flip a coin that's just weighted a little differently within group and between group. And so all I've done there is construct a new random graph where I've partitioned the pure and these randoms by varying the level of ties in each of these different types of cells. Now, as you can see, it still doesn't match very well, right? So this is a better match. I've matched the mixing matrix, but the structure still isn't right. So this is still a much more diffuse sort of hairball graph, and there's something patterning the network in the observed case that's not captured by just the mixing matrix. So we need something else that isn't there. So in this case, we notice that the degree distributions don't match, so maybe we need to do something like that. And that's the kind of logic that we're going to do. We're going to say, if this works a little bit, then maybe something else like this would work better. So I'll condition on both race and gender. And if that works well, then maybe I'll find some other series of buckets that I can put people in, little compartments that if I get down far enough and I structure all the relations between it, and you of course recognize from yesterday that I stole this graph from somewhere else, but conceptually you get the idea that maybe that would work. Or I could ignore the buckets entirely and just think of something like a latent space and say that nodes, I'm going to define some space such that nodes that are close to each other have a tie and nodes that are far apart don't have a tie. And that's the mental process that we're going to go through when we think about building these kinds of models. We're going to construct sub-random graphs that we've constrained in a very particular way so that the probability mass, if you were to draw a graph from the space implied by that model, looks a lot like the model the graph we've observed. And that's the notion of fit that we're going to use. So the notion of fit and the notion of hypothesis testing is, can we generate a network for which our observed network would be a reasonable draw from that distribution in the population? So whatever constrained distribution of random graphs that are possible in the world out there, it should be the case, if we've done our modeling well, that our observed graph would be a plausible case drawn from that distribution. And so that's the fit structure we're trying to go with. Please.
Just so I make sure I'm following, is this primarily for the purpose of hypothesis testing, not wanting to have some comparative
Yes.
random graph population to draw from that matches vaguely our model?
Yes. It's
for hypothesis testing.
It's for hypothesis testing in this particular sense. And the logic is that if I'm really clever and my theory is good, I should know how to condition the space properly. So for example, I thought that race should condition this graph. Turns out that theory is pretty wrong. That something else might.
Condition, do you mean like you're throwing it in, using it like a linear probability sample analogy? It's like throwing it in as an additional variable to create that constraint.
Yes, exactly. And I'm going to walk through a step of that.
Like mapping the new words to the whole word.
Yes, fair enough. Yes. Thomas.
Yes, if you find a good model that when you observe the network we determine whether it's a good model by checking whether the networks you observe could be probable examples drawn from that distribution. But how do you make this assessment?
we do it computationally. We simulate a whole bucket load of networks from the model and see if all the moments of our observed graph fit squarely in the middle of those models. And as you probably know, that might not be a perfectly good test, because it might be I picked the wrong moment to compare. Right. But that's the way we do it in general. All right. So the version of this version of that model is exactly what I've done here. So this is the sort of conceptually buckets, buckets, buckets turn into spaces. And so the space model was developed by Peter Hoff and Mark Hancock and Mark Kruszycki. Other people call these Hoff models, for example. Peter Hoff is in our stats department here. We stole him from University of Washington, where they worked with Rafferty and Hancock at the time. Pavel's now in Australia, if I remember correctly. And so the model looks something like this. And I know that everyone hates the equations in this room, but it's worth having a little bit of a look at it. And so most of us as social scientists are used to thinking about a logit model or a logistic regression. That's how you predict a binary dependent variable. And so the logit predicts the probability of a tie between I and j is conditional on a set of features, some overall density features, so the number of ties in the network, and the distance on two imaginary variables between I and j. So that's all this equation says, is that the closer we are together in that space, the more likely there is a tie, and the further apart we are, the less likely there is a tie. And the beauty of the latent space model is we're going to make z up. Like z doesn't mean anything in reality. It's a variable we're just entirely going to make up. And so this is an example of what this model kind of looks like. The Samson Monastery data is as a traditional old style data that comes in the network, and it's a stochastic model. And so we end up trying to find positions in the latent space that predict the likelihood of a tie. So we just keep adjusting your assignment. In this case, I've told the model there's 2 dimensions. And so I keep adjusting the relationship between these 2 dimensions and each person's value on each two dimensions until I've fit the best likelihood that we have a tie is corresponding to the space in that set. The stochasticity of it is generated that each node could be in any one of these little cloud of spaces. Right? So that's what I mean by saying it's a stochastic process. The beauty of these kinds of models is that they're really, really flexible. And so in this case, I have a 2-dimensional space, and you just fit the model. I could fit a 3-dimensional space. I can add non-homogeneities to the space. So I can say instead of having just 2 dimensions that are completely uniform, I have 2 dimensions, and there's 2 groups that are built on, or in this case 3 groups, where the distances within are weighted differently than the distances between. So all of these is built into the model, which is kind of fun. The beauty of this set is that it greatly simplifies the modeling exercise. Because we're going to go through in the next model, which is not a latent space model, in which you have to specify what builds into this conditioning. So the beauty of this model is that it really does just finds the best fitting imaginary variables, z1, z2, that distance predicts tie values. And so it almost has to fit, right? But there's no sense of which this means anything socially. Right? So there's literally nothing. So it might be that this is race, it could be age, it could be income, it could be whether or not you howl at the moon in the middle of the night. Like, we have no idea what it means. All it means is it's a good predictor of a tie being there in the distance of the space. Now, if every methods problem is a theory problem in disguise, it might be that this teaches you something, that when you look at the space, you learn something. But it might also be that it just helps you control for things. You can do this with weighted or binary ties, so it's really become a very flexible modeling sort of system. My favorite use, just in the interest of time, for latent variable models is when I don't know what's driving the disruptions of the model, but I care about something like homophily. I can throw in a latent space and then test for homophily on my others. And the latent space essentially soaks up all my unknown variants, and then I can test whether or not the homophily effects work independent of it. All right. Now let's spend a little bit of time thinking about the logic of how we might build up a more specific model, where I don't want to let the latent variables define the ties for me, but I want to actually have some control over what drives the ties in a network. And so this is not an exact analogy. I'm playing a little fast and loose with it, and I'll correct that in a minute. But just start with the idea that you have a standard kind of a logit model, and you're trying to predict ties on a matrix. And so in this case, we could imagine that the probability of I've observed a graph that looks like this. And so in this case, the ones are bright red and the zeros are blue. And so that's my observed data. And I'm going to say, what things can I add to this model that would predict the probability of those ties being there? So the first thing I could do is just have an intercept. All right? And so this is what a simple Erdos random graph is. And so I say the probability of a tie between I and j is a function of some constant. And in this case, that constant equates to a probability of 0.24. That's just the density of the graph. So all I've done is given you an equation version of what the density of the graph is. Now, because this is a logit model, this thing is actually on the log odds scale. So the coefficient you get out of the model is going to be something that's largely uninterpretable to you in the probability space. But you convert a log odds to a probability by taking that value and divide it, exponentiate that value divided by 1 plus the exponentiation, you should get 0.24. Right? So that tells you what it is. Now that model does something, right? It tells me if I were to draw 1,000 random graphs from this probability distribution, I would get a series of graphs that on average have the same density as the graph that I observed. But I wouldn't tell me anything else about who's there. So I can do a lot of things to this, right? Let's add a row effect. So now I say that we have a probability of ties across the row versus ties across the columns, or jointly. And it turns out that if I know a row effect, I know a column effect, right? That alone has now constrained the sample space a lot, that the probability mass is really falling. It's a high probability that this thing should be a 1, and in fact it is a 1, whereas this thing should not be a 1, and in fact it's not a 1, right? And so very simple volume effects of out degree and end degree on an asymmetric or a directed matrix like this can get you a long ways. It doesn't get you everywhere. So again, the bold ties in this case are the observed graphs. And so you can see in this case that these are real ties in the observed graph. That's a real tie. But my model, based just on volume effects, don't do enough to make those high probability ties. And so we will often then add some other feature. Right? So in this case, I've just magically called it dyadic similarity because I've made up this example. And the dyadic similarity is something that we think socially predicts the likelihood of a tie there. And so in that case, because I built this as a toy example, it did a nice job of hitting it, but it also never hits perfectly, right? And so you're still going to have cases where the model doesn't fit and cases where it predicts ties that aren't there. So that's fine, right? And many people will argue that, in fact, those ties could well be mistakes. If your theory is good, if you understand the social process and you generate Q here as something that's socially meaningful in your setting, then the fact that I randomly see a tie that shouldn't have predicted to the model is kind of interesting. You might ask yourself, well, why did that tie there? Where did it come from? But on average, in repeated samples, this graph is really close to the graph that we would predict from the probability set. That's the thinking anyway. And so these models are, in fact, where we end up when we ask this modeling class called exponential random graph models. And so substantively, this approach asks whether the graph in question is an element of the class of all random graphs with the given known elements. And so all the elements in this set are fixed. And so in this case, we have a simple 4-parameter model, and those 4 parameters are, an exponential family predicts the probability of this set. So now that was, the reason I say you don't do this is because actually fitting a logit to this is violating a bunch of the assumptions of the thing, and people get their hair all out of water, but so don't do that. So instead we do the right thing. And the right thing, and the reason that it's wrong is because you need to have a proper probability where all the elements sum to 1. And so the model is set up like this. The question is, what's the probability that the graph I've observed is an element of the class of all possible graphs of this given class, and that class is defined by an exponential function of some set of graph statistics times coefficients normalized by a constant. All right. So that's all it is. Now these graph statistics would be the in degree on the columns, the out degree on the rows. Those would be your row and column effects. Or it could be the dyadic similarity, or it could be homophily on race, or it could be a whole series of different things. The real bugger is that K there, that little normalizing kappa of theta there, is that thing is unknowable on graphs that are of any particular size. And so by and large, it's really hard to come up with a normalizing constant in the form that you have here. But some really clever folks came up with this notion that it turns out that if you do a little bit of clever algebra and you think, well, I can figure out what this model looks like if I condition it on each individual cell in turn, and I hold that cell as either fixed or not, then it turns out that this whole thing that we care about is a function of the difference in the graph statistics, given that the tie is there or absent for all possible ties in the network. And so if you go through and for all possible dyads, do this little funky calculation where you take the graph statistic, calculate it with the tie forced to be present, calculate it with the tie forced to be absent, take that difference, that now becomes your independent variable. And when you do that, magically your normalizing constant disappears because they're on both sides of that feature. That's kind of fun because that allows us then to turn this in to a logit model. And so when you have that, in theory, you can make this thing work. And so the steps in doing this process are that you have to specify the model, you have to fit the model, you have to make sure your model actually converged. And if you didn't, right, so if your fit is not good, you re-specify the model, you keep doing this until you get it right, and then you publish your paper, you get tenure, and you go on to life and success. Now, please.
So the whole purpose of this is just for good as a fit? Or for testing your significance of your
Yes. So it is for testing the significance of your predicted variables, in the sense that if I add a variable to the model that has no effect on fit, then that variable has no social relevance to the set.
And so Ergo is referring to
Exponential random graph model. Okay.
which is like an underlying statement.
It is the class of all of these models. So the exponential random graph. So this is an exponential family of models, and so it's the exponential random. The fact that x is a graph, and this is a random probability. So that's what a random graph model is. So this is the exponential family of random graph models because we build it.
So this would be like generalized linear model.
Very much.
So
That's the beauty of
so
this.
it's like,
Yes.
it's actually a word that's referring to a group of things.
Yes. And that's great. This is absolutely right. And you're going to see, like after all this architecture, when we get done at the end of the day, we're running a logit model. So, which we know and we understand, right? So it's what all of us do, like every day.
Based on different distribution assumptions.
Even the distributional assumptions are not so different. It's the way you construct the independent variables that is a little bit different. And it turns out there are two different classes of these ways we construct these variables. So that's what we're. No, the ergom, all of them are ergoms. It's just that some of the variables you construct exactly like you would construct in a logit model. These are known as dyadic independent variables. And others you have to construct to figure out things that are dyadically dependent. So the score that I have depends on the score that you have. And that's where the complication comes in. All right, so we have these models. Now, these models end up looking like a logit model. So we're going to say the probability of a tie is a function of a probability of features of the dyad, features of the subgroup, and features of the graph. And so we have a whole series of things that the probability of a tie depends on. And it turns out that there are a huge number of these z statistics that you could possibly calculate. I'm not going to go through most of them. In fact, I'm going to barely touch the tip of the iceberg of what kind of variables these could be. But the good news is at least since 2023, they now have this wonderful table that lets you go through and figure out what kind of term is in each of these models. And so it's there, it's part of the ergom cross-reference table, and you can look up for each kind of graph you have. But the standard kind of parameters that we fit in this sort of our world that we play with, so we tend to have homophily features, and so these are characteristics that you might say are usually done with either a node match or a node distance feature, depending on whether it's a quantitative or qualitative number. And so if you want to say, if you want to know whether or not race or grade or gender conditions the probability of observing your graph, you would say node match race, node match gender, node match grade, right? So these kinds of features are added to the model. We might also have this notion that we think that a friend of a friend should become a friend, and my friend of my enemy should be my enemy. And so that's a social balance process. And a social balance process you would estimate in this language using a transitivity term. Don't use a transitivity term. Logically, you would think you should. Turns out it'll crash. Instead, we use something like a transitivity term, which is known as a GWESP term, which I'll explain in a bit. And there's lots of these. So we might have other kinds of clustering features or particular path structures. Craig was nice to point out the romantic network. We had a theory there that said that people wouldn't form 4 cycles, so we can put a 4-cycle term in the model, and we should get a negative coefficient on that term. And in fact, you do. So that's the kind of process that you can play with. So I'm going to walk through an example, and this is the example that's in the .r file and the ergom data. It's a small school sample. It's a network of 71 nodes that have all 12 grades. So it's a really small rural school in eastern Pennsylvania. And it's nice because it gives you a chance to see what the network looks like and how these models are fit. So this is the what the network itself looks like. And I'm just going to go ahead. I'm not going to do that. I'm just not. If you want to run it yourself, go and have a look. It's in the code. I'm going to go ahead and just go through the slides to describe it now. Are you kidding me? There we go. So the way you specify these models, once you read in the data, and it's your standard sort of StatNet object, you read in the model and you specify it as an ergom, where you take the school network in this case, which is what I named that graph, and I say it's a function of an edges parameter. So that's just an intercept-only model. So if you do that and you go through and you look at the resulting graph, you'll see that I get a strongly negative edges parameter, minus 2.72 in this case. That is a non-interpretable number by itself, except that if you convert it to a probability, you get the exact same probability of the graph itself. So that's all it's doing. So this is literally that first model I showed you of an intercept-only model. This, if you wanted to generate Erdos random graphs with a known density, you could just do this. You could flip it around. Now the beauty of these models is once you've estimated the model in ergom, you go throughout, you can then ask whether or not this model fits and you can simulate from the model. So I know the ergom model doesn't fit, so I'm not going to bother describing that to you. But instead, I'm going to define a variable on the network that's in degree, a variable on the network that's the out degree, and I'm going to re-estimate a new model, which is the random graph, so the school is a function now of the edges, plus an attractiveness parameter for in degree, and an expansiveness parameter for out degree. So this is a column effect. So the incoming ties is a column effect. I'm going to say the probability of a tie should increase the more my in degree increases, and it should increase the more ties I send. I then ask the model to summarize. I get a good enough a fit, and so forth. And so this is what that model looks like. And as you would expect, we see that the higher my in degree, the higher the likelihood that I receive a tie. The higher my out degree, the higher the likelihood I receive a tie. I send a tie, excuse me. And so these are statistically significant. And these statistical significance are determined by an MC-MC kind of change through a process that are not worth going into here, but that's the model. So you can see the score that comes through on this set. Now, what you'd like to know is maybe that's sufficient. Maybe that's all that's going on in my graph is sender effects and receiver effects. And if that's the case, I can figure that out by doing these goodness of fit plots or simulating a network from the model. And in this case, that's what this little line does right here. It says, let's simulate from model one observation. And if I wanted to simulate 1,000 observations, I would just trade one with 1,000, but I was lazy, so I only wanted one. And so I look at it. And so I just plot this simulated network now, and you can see that this thing doesn't match that structure. Right? The observed structure we had those really tight clusters. This one doesn't have that. There must be something else going on. So let's keep building the model. Here's another version. Right? So now from model 3, I've skipped a couple models at this point, so I'm sort of going through this relatively quickly. And so in model 3 now, I said let's have my edges parameter. Let's have my in-degree parameter, my out-degree parameter, and now I'm going to add a whole series of homophily parameters. So I'm going to say these kids match on grade, they match on gender, they match on smoking behavior, because I'm sure it's like Craig's network. And then I also say that there's reciprocity in the network. So you can't let these ties just fly all over the place. If you nominate me, I nominate you. And so let's have a look at that model. We run that model. It goes through and it does its thing. One of the things you'll notice if you actually run the code that's on the server is that the prior models went really fast. That's because they only had independence features. The mutuality term, that term can't be well estimated with the logit model. You have to estimate that through this resampling chain process. And that means the whole model has to be estimated by this MC-MC chain. And so the convergence time is going to be higher, a lot higher, actually. And so if we do that, we see that all of these features seem to condition the graph. You have a higher probability of a graph depending on these various features. This would tell us our grade homophily, right? In this case, this 2.5. Oh, wrong up. And yeah, so then if I go through and, yeah, I'm on the same kind of model. What did I do? No, I added, so yeah, I'm going a little fast. I'm done at oh yeah, they're all the same. So they're all the same. So we have until 1. Okay. Because we eat lunch at 1. All right. So so here I'm just running. I'm going to show you what these models look like in real time, just a little bit. So there's running all the models above. There we go. So that's now giving us this final set of models. Come on, keep going. There. So this is what you're going to see when you see the models run. And so when it's doing any of the actual sort of more difficult estimations, it's doing a series of convergent steps. And it's trying to find the best, you tell it some maximum number of total MC-MC chains that you want to run, and each process that's going to re-estimate and resample and so forth. And finally it gets to the end when it converges at the set. And in this particular case, I ended with this model that I just told you about, right, this model 3. So we'll see if we get the same answer. One thing that you will notice is that sometimes the coefficients will be slightly different, so it's a stochastic process. In this case, I had 0.57 for that, and yeah, so you'll notice in this case, where, for example, the mutuality effect that I estimated the other day when I ran this was 2.3. Here it's now 2.34. So they will always vary just a little bit. If you really care about something to the second decimal point, increase your iteration set. But the model looks like this. And when you do these goodness of fit statistics, and this is why I wanted to show this one first, what I'm doing is I'm going to now, we're going to take this model object and these coefficients, and we're going to simulate 100 different networks from this distribution defined by this equation. And once that gets done, we can plot it. And the way the plot works is that for each statistic that you do, and there's a set of default statistics that they come up with, but you can specify any graph statistic that you could put in the right-hand side of the equation you can test against. But the standard rule is you want to test against a graph statistic that you didn't put into the model. Because definitionally, you better fit the parameters you put in the model, because that's how the model was built. And so I'll show you that in a second. And so in this case, the observed network, if you look at the distance matrix, the geographic distance between all pairs of networks, about 5% of the nodes are 1 step from each other, about 15% of the nodes are 2 steps, about 18% or so are 3 steps, and that's the distribution of distances in the networks, and some set of nodes are isolated. And then if you look at The box plots, that's what the model would simulate. And so the model thinks that as the class of graphs defined by this model would predict a distance distribution that is somewhere in this range. And so what you want is this black line to be inside that set. That would say that this model captures the distance distribution in the network. Now, it's also, in this case, you see I don't do a particularly good job. I haven't fit the number of isolates, so my number of isolates is lower than the number predicted by this graph. And it looks like the random graph has generally a shorter distance distribution than mine does. So the actual observed graph is spread out further. Go ahead.
Talk through like the rationale of why you use like a Monte Carlo simulation versus like a grid search or gradient descent method.
I can't talk through that. So there's Pavel and Mark have spent untold hours figuring out the optimal solution. I think of it because the original one was a very simple Monte Carlo chain that was literally the coin flip on all possible edges in the graph thousands and thousands of times. They've now come up with a much faster method, orders of magnitude faster, which is doing something like I think you just described, but I don't know which. So, but look, if you go through here, so there's other statistics that are often of interest. This is the edgewise shared partners, which is the number of times two connected nodes share a third. This is what the distribution looks like in the real graph, and this is the distribution in the model. It's close, but it's not very good. In this case, you can look at the n-degree distribution. You can see we didn't fit that particularly well. It's kind of in the area, but you'd like to see a bit of a drop here at 5 that's not there, that we can see in the real graph. And the same thing when you go over here. So this is the out-degree distribution. Now, I'm asking it to fit, I fit a single parameter to the in-degree and out-degree, a linear parameter. So this model has to kind of have a smooth distribution over the distance by the way it's defined. You can put different functional forms to something like in-degree or out-degree to make it fit a little better. Now, this is why I say we don't fit to the model in the statistics. Right? So these are the statistics that are in the model. I do a great job. Right? I fit those almost perfectly. And the only reason it's not perfect is because there's a little bit of stochastic noise in the element. This is the only reason you have this plot is to make sure your model converged. If this isn't true, you have to go back and fix the convergence in your model because something's screwed up. So I was trying to figure out, so what I like to do is do these features, these plots, just like I said as well. But then because I find especially for small networks, the sociogram is more intuitive. I like to simulate one of the graphs from the network and then plot that network, and then I can see what it looks like, just like I did a minute ago. So this is the kind of graph you see when that happens. So I was looking at this model, and this model is actually a pain in the ass to fit, to be honest with you. If you go through and do lots of things, it never really fits quite well. And I realized that part of the issue is that we were just matching on grade. We said if you and I are the same grade, there's a probability we should be a tie. But it's also the case that if we're in adjacent grades, we should be more likely to meet than when we're distance grades. So 7th graders are more likely to meet with 9th graders than they are with seniors. So we have both a matching qualitative, same grade or not, and a gradient on the distance of grade. And so when you run that model, and let that go, you can see, now all of these things at most 60, all of those are things that you can change as you go on and decide to do it. The model goes, it goes for a while. And it's taking time now because it's doing this search process that you have to try to find the best fit to the model. Then figures out that. Look at the model. And as you might expect, it is the case that the further we are in the grade space, right, we're less likely to be tied to each other. And so then, if I added an H there, this is why you don't do things live. So again, if I just do that, I run the goodness of fit again. You can see I still don't quite get the geodesic distribution particularly well. I mean, it's not awful. It's a little better than it was, but it's too far. I get the edgewise shared partners pretty well. My in-degrees start doing a little better. Out-degree in this particular case wasn't as great as it could have been. But qualitatively, if I just simulate one of the graphs and then plot it, you can see I'm getting a lot closer. Right? So now I'm actually starting to see this segregation of the freshmen on one side, the seniors on the other, that wasn't there before. So that process allows you to see what's going on. Now, part of the reason that this model is not fitting, and particularly the geographic distance feature, is that in a random graph, there's no closed triads, or there's very few closed triads. And so it ends up being the case that when I have a choice to send a tie between two people, of this case, of the same in degree, the same race, the same grade, or the same smoking status, I'll just pick them at random. But if one of them is tied to my friend, I should pick that one over the other, and that would lower the overall sort of set of ties, and it should sort of move all those geodesics back into this clustering set, which then should create greater distance in the network. So in order to get that, you need to add some element of a triadic closure. I'm going to point out, just because it's here, I've been fitting a homogeneous grade feature. You can say that there's a heterogeneous grade feature. That's what this diff equals t function is. So I can say that we're all going to have some matching on grade, but it might be stronger for seniors than it is for freshmen. So that's what the difference feature says. There is, in fact, a little differential homophily in this graph, but not particularly well. Now, if you go into this, you'll see I have a note here that says I tried a bucket load of things to try to get this model to fit. I built this off a graph that Jeff built earlier. And at the end of the day, it took a long time for this model to go. So I'm going to show you a little bit about how this thing ended up getting fit in the end. And so what I ended up adding was the same things we had before, so our intercept term, our matching terms. It turned out that the differential matching on grade didn't seem to make a huge difference, so I shut it off here just to get some convergence things happening. I have some attractiveness of smokers, some expansiveness of smokers. Again, the gradient on grade. I fixed the number of out-degree isolates, so the people that sent no ties, I just put a parameter in for them. And then I have this triad feature. And what this does, the triad feature says, I'm going to go and run it, and I'm going to explain it, because you're going to see it's going to take a while for this model to run. If it runs. And so what it's doing now is trying to fit all those things simultaneously. I've set up some things to try to help it along a little bit, but it's going to keep going as we go here. And I'm going to let that go in the background, and we'll come back to it if it converges. So if you go through and look at this model, as we go through for the better fit, each of these models is a little bit better. So this is the model that's ultimately, I just said, to fit. We're just trying to run right now. And you can see that the geodesic distribution, now starts to fit. And that's because by adding closed triads, I've essentially extended the distribution of distance in the graph. So that's nice. But you'll notice I didn't put transitivity in, I put in GWESP. So what is GWESP? So GWESP is an acronym for the geometrically weighted edgewise shared parcellars. So what does geometrically weighted mean? Intuitively, our theory is that transitive triads are good. That if A is tied to B and B is tied to C, then A should also be tied to C. And so if you say, I'm going to have a positive coefficient on the number of triangles in a general linear model, what I'm implying is something that looks like this. That is, what I'm implying is that the more of this I have, if it's good to have some closed triads, it's much better to have lots of closed triads. And what happens, we discovered over the course of a long period of sort of field explorations of these models, is that you end up with a snowballing effect. That once you add something like a transitive triad feature, that because the model thinks that the marginal return to each additionally closed triad is equivalent, it's just going to keep adding closed triads. And so what you're fundamentally going to get are graphs that have complete cliques, everybody connected to everyone else, or completely empty, and the mean of that will be the number of closed triads you have in the graph as a whole. And so the model will fit in the global sense of the expected value of the number of triads is right, but on any given draw from the probability distribution, you either got a complete network or an empty network, and it's a mess. That's known as a degenerate graph. And it turns out that it's a problem with model specification. It's because, in fact, we don't care. It's not true in social life that networks, if you have closed triads, you get more and more and more closed triads. There's diminishing marginal returns. And that's what geometrically weighted edgewise shared parcellars means. It means that for my really close ties, for the people that matter the most, that I have a high probability of tied to, I'm going to be friends with them. But I can't be friends with all of my friends' friends. There's some limit at which this happens. And so there's a geometric decline in this as we move forward. And so that's all the GW means. So GW is geometrically weighted. It turns out that weight, it did finally finish. That's great. It didn't finish. I was running this last night. It didn't finish. I had to stop it. I was kind of hoping I could show you what that looks like. But so in this particular model, you'll notice I have a couple of other parameters. And so there's a decay function, and you ask whether or not that's fixed or not. What that decay function is the speed at which this thing curves and flattens out. So I can let that thing be close to linear, or I can stomp on it really quickly, right? And what you would like to do is let the model figure that out for you. But if you say that fixed equals false and you let it figure it out, it takes forever for the damn thing to converge. And so my experience has been pick a number that's reasonable, somewhere between like 0.2 and 0.6, and it usually works just fine. If you really find that, I know that's ad hoc and it's like you hate it, but it works. And it just doesn't matter because you can either put the weight on the coefficient for the whole term, or you can put the weight on the coefficient for the decay parameter. The two are going to balance each other out eventually, and so it's fine to do one or the other. That's effectively what you're doing there. So when you get that done, let's do a summary of this model. You'll see that in this particular case, that there is a positive return to closed triads. So it's the case then that as for each additional triad up into a diminishing return, which is defined by that, you end up with a slightly higher likelihood of having closed triads. If I then go into the model, is that the right one? And say, let's just give me a plot of my goodness of fit. Okay, I have this already printed out. I don't have to run it again. Well, going the wrong direction. Told you I should know how to use PowerPoint by now. So this is what that model looks like that I just estimated. And so it fits reasonably well, right? Like I said, we've matched the degree distributions. The distance distribution now is what I want. That seems to be fine. And then qualitatively, it looks okay. This particular draw from the distribution, I have a few more isolates, and my gray nodes are kind of spread all over the place. So my guess is there is some differential homophily there that I'd want to fit a little bit better if I really cared about that. But to me, this seems to work pretty well. Substantively, you read this table the same way you would any other logit model, right? So this is your hypothesis test. You say, my hypothesis was that there would be an age gradient to grade, and that people who smoked there'd be homophily on smoking. And in fact, this model fits best if I have a term for smoking on node matching, and that suggests that these kids are sorting on smoking, even net of sorting on grade, gender, and their distance in grade. And so there's leftover homophily on smoking, net of these other features, that adds to the fit of this graph. And so that's how you would interpret that as the hypothesis testing side. Now, there are a couple of things that can go wrong with this. There are a lot of things. I also often will test triad distributions and things like this just to get a sense of higher order features that seem to match. But one of the things that will go wrong often with these models, and particularly the more complicated they get, is that you'll be sitting here, you'll be running your model, it'll be going fine, and it'll say, I'm on iteration, usually it's way up here, it'll be on iteration 3 of at most 60, iteration 4 of at most 60, iteration 4 of at most 60, iteration 4 of, it'll sit there forever, and it's because it's got stuck. And so these things will get stuck, and it won't necessarily pop you out. Sometimes it does, it has some nice error handling in there and gets stopped. And so your best solution, if you sit there, if you've noticed that the time to the next iteration as you're watching it is a lot longer than the time to the prior iteration, hit that stop button up there, start it over and try again. That's the first thing. If it fails twice, you have a badly specified model, you need to do something different. And so you need to go in and try a new set of parameters. Now it turns out that one of the things that has made this thing wrong is that there is an easier way to fit the model, which is to use this thing called stochastic approximation as the method that you're fitting. And this is a different optimization method than the standard chain method that they're using. And when you run this, it almost always fits, and it goes a lot faster, right? And so the trade-off, there's no free lunch, right? And so the trade-off here is that you're going to get somewhat less precise estimates. So you're going to have a little more noise in the model. But the trade-off, particularly if you're doing simulations or other kinds of large-scale models, here I added the differential homophily back in, it's just so much faster. And it's faster, and B, it's more robust. It doesn't just hang there forever in the way a lot of these other models do. So again, in this case now, I've added a couple other things I should have told you about them. So this is differential. This is what differential homophily by grade looks like. So now you'll notice we have a different coefficient for each grade. Most of them are essentially the same, except for the seniors. So the seniors are much more likely to be homophilous with each other than are the other grades. It turns out in the new specifications, what I could do is say have two classes, collapse 7 through 11 and fit 12 separately. So you can go back and forth and fit that. Go ahead.
We have a lot of parameters in the model. Is there any fear of overfitting? So let's say you compare this model now to a different school, but fits this, whereas the other school does. The next school will well.
Yes, that's a very good point. And yes, there's all kinds of issues with that because you're only fitting to one observed case. Right? So if you're fitting in one observed case, you can tune it to be exactly right. And so this is why I like having data where you have multiple schools, and so you could do just that. The one big asterisk here is that this convergence issues get to be a real pain in the ass across lots of different schools. And so you might find that one model just won't fit in all the schools, and that the model that will fit in all the schools fits none of them well. And so that's the trade-off so between making the model really sort of tailored to a given setting versus not, is that the models that will fit are often not the best models, and the models that fit nicely in one setting might not fit in another. And so there's a lot of work you have to go through to make sure that those things, that just doesn't happen. Okay. I've noticed a couple other features here. I added, these are opposite features. So this is the geometrically weighted edgewise shared partner. That's the likelihood that we're closing triads. The geometrically weighted non-shared partners says that I'm avoiding triads that are open. And so we're simultaneously sort of getting a double whammy here of closing triads when I have the opportunity and avoiding making ties that would create an open triad. So it's a nice feature of being able to do both of those things. So there are multiple other ways you can do this. Let me go back a slideshow from the current slide. Back to where I was. So that was the model I just showed you. Now it turns out that one of the problems with those kinds of models, and it's not just an overfitting problem, it's just a complexity problem. Oh, sorry, Tom.
Sorry to interrupt you. So what's just to understand the overall context here? So you could of course find a model that is so precise at the end it just spits out the exact same graphs that you observed in the school, right? So you make the distribution so tight, you add so many parameters that you just always get the same number.
Right.
Exact same. So what's the goal? You want to generate a certain set of networks which are similar to the one that you observed in the school, but how similar should they be?
Yeah, so you want them to be, that's a theory question. It's like, so the model, for most of us in the context of social sciences, the goal is to figure out whether or not the homophily features or the social balance features are doing any work in terms of conditioning that graph. And so we don't actually care about fitting it exactly, but we don't want it to be wildly wrong. And so the distance between wildly wrong and fitting exactly is a judgment call. And it's entirely up to what people are doing. Now, there's one element where that's not true. And that's when you use these models. These models are currently, I'm estimating them on a complete graph. Where they're really valuable is when you're measuring them on samples of graphs, where I have lots of little chunks of networks, and I want to simulate what the whole network looks like. Then you want to do a pretty good job of fitting what your observed stats look like so that you can interpolate beyond those stats to a wider network. And so there, the goal is often, for example, in our village networks with the work with Charlie Nunn, there we've sampled about half the people in the village. And we'd like to know what the disease diffusion risk looks like for the village as a whole. So we fit a model on half the network and then extend it by simulating to the rest of the network. So we upsize the network and then change it out. And there, what you want to do is simulate networks that you think are plausible representations of the networks that you sampled. Now, they might still be overfit. It's still a judgment question, but that would be the goal in that case. Does that help a little bit? A little bit, yeah. So the reason you would do it, now one thing that you would often do, or not often do, but I think that I recommend doing, is that if you really only care about testing whether or not there's homophily on some observable. So I have some theory that kids who smoke hang out with each other. It's not a particularly deep theory, or that there's node matched by grades. Then oftentimes your life is made a lot easier by just fitting one of these latent space models to it. Let that take up all of that sort of idiosyncrasy with the model, and then only test the thing that you care about. Right? So I'm going to let the model fit with the latent space model in this case, and then I'm going to see whether or not there's, after I've given the latent space everything it can, is there anything left over for grade versus sex. And in this case, it turns out, oh, I'll go back up, I lost my coefficient. It turns out that the grade still matters, right? There's still additional variance left over in the clustering on grade that the latent space can't capture, but whatever's going on with smoking is well captured by the latent space. So there's nothing else left over in terms of the homophily of that. Now, what does that mean? It might mean that the latent space, that one of your z variables is smoking, and you don't know it, so that's the trade-off there. But if you had a strong signal from smoking, it should still be there. It's above and beyond whatever's simple. And again, you can also go back and resimulate out of the latent space models. For some reason, the network object that's simulated out of the latent space model drops all the attributes. So you have to repin the attributes if you want to color by it. But it's the same kind of process in terms of fitting the models. Please.
So you motivated with these exponential random graph models also by the fact that you can sort of write on the community distribution very nicely. So I mean, some of the deviations you see here probably just from the assumptions, from the basic assumption of your model, right? So the question is, there are some general arguments that sort of networks that cover nature sort of should be of this exponential random graph type, or can you, like, if you add more and more parameters, basically reproduce any sort of nature of networks, or what's the...
So there are some. Carter has a really nice paper that came out just a couple years ago where he goes through and he asks a question I think similar to this, which is there are some underlying functional forms built into the exponential random graph model and some of the functions of the shape of that form that he's able to adjust. And when you do that, you do get different results. And so there are different ways you can tune to where you're getting at. And he's making the case that these models, sort of if left to their own device, are making sort of hidden assumptions about the structure of the underlying graph. I think practically, for most of the work that people in this room want to do, those assumptions don't matter that much, because once you add the coefficients back in, you can get to the same spot nicely, and it has a relatively nice test. But I think that if I were using this model to fit a protein structure or something like that, that I might want to think more carefully about how that's generated. David, do you have a reaction to that? I know you've thought about these. Okay. So that's the way these models end up getting fit. There are a few things to keep in mind. The models are very sensitive to model specification, so you do have to spend a fair amount of time thinking about that. Complicated models are difficult to fit, right? And so you need to have some. The package was built, I think, with a set of defaults that are not bad, and I think there's good reasons. Like Carter and I were emailing here just a couple days ago about why this is the case. But if you ask guys, I have to give these people some advice on what to set in terms of the burn-in and the number of iterations and such to run. And this is his advice. This is literally a direct quote. I should have put a quotation mark out of it. But essentially, the default number of iterations for the chain size and the sampling rates is much too small for most of the graphs that we're fitting. And so if you were to take that same graph that I was running, which I set to have a burn-in and a chain size of about 2 to 3,000, you could easily set it to 16,000, or if you take the really high end, over 1 million, right? So if most of us are not patient enough to wait for that kind of process, which is why I like the stochastic approximation method, But if you find that your model's just not converging well, or you're getting MC-MC chain plots, diagnostics that look really non-stochastic, then first thing to do is to make sure your model looks, is substantively reasonable. And if it's not substantively reasonable, if there's something that obvious like grade distance in addition to grade category you should add, do that. But once you've done that, I'd probably up your iteration size. Your iterations are probably too low. All right. So all of this that I've discussed thus far have been on the analogy of a logit model, and we've been working with binary graphs. Turns out that that's not a constraint. There's lots of other sorts of features that these models have now been generalized to. So the first is dynamics. So we now have dynamic networks, which are tergums or temporal ergums, or sturgums, which are separal temporal ergums. A separal temporal ergum means you have one set of parameters for forming ties and another set of parameters for deleting ties. You have what are known as a relational event models, which are ergum-like, but in continuous time, so you don't have a fixed or very narrow discrete time. Scott Duxbury, who's talking this afternoon, is going to give us an overview of all of these models, and he has a great new book on this set of features. There's also a whole series of extensions to different types of networks. So we have bipartite, we have models now for bipartite networks, for ego networks, for value ties, for rank ties, for multiple classes of networks. So if you have multiple schools in your data set, for example, and for multi-relational networks. So there are now specialized models for each of these features. There are Bayesian versions of these models. And so there's a Burgum package out there now for fitting the models and then doing posterior estimation on these models. There's a whole series of features on that. More practical is that there are a series of new syntax features built into the model. The new 4.x versions of ergum have a whole series of on-the-fly specifications that you can do to the model that makes it easier to specify models that we might care about. And so you can do things with character searches, and if you're a tidyverse kind of person, you can build all of the functional passing that you would do in tidyverse, you can do in the formula object itself. You can also do these things where you now add curves or other kinds of functional forms to the model as a specification. So if you want to have a peak grade, for example, at which you think that ties would form, then you can add that as a say a polynomial to the graph, which you do in normal grades. You can also, wrong graph. There we are. You can filter things, right? So you can sort of decide, I'm going to only apply my graph to one thing or another. I like this new S set of operators, these subgraph operators, which effectively allow you to fit different parameters to different parts of the model. So I could say that I have a general set for everyone, but then for some subgraph of the model, I allow the parameters within that group to be slightly different. And so that allows you to essentially it removes what's known as the homogeneity assumption in these models. So right now it assumes that everyone who's in the same parameter set has the same covariate set has the same parameter effect. And this allows you to have a little bit of variance in that kind of set. You can also add, there we go, you can add interaction terms. And so I can say that the probability of forming a tie based on my grade is conditional on my sex. And so you can have interaction terms by categories. These have to be dyadic independent features. You can't do this with the triadic effects or other kinds of mutual effects. But for most of the kinds of questions we care about in terms of interaction terms, these can be quite useful to think about that. All right, so those are ergums. Questions? Any other thoughts on those before we move on to flipping it now and thinking about the network as a dependent variable? And I'm going to give you all of like 10 minutes on that before I go on to the next. Please? Is that a question? All right. Awesome. Okay. So oftentimes we're interested in using a network to predict a different kind of an outcome. And one element that, one way that people have done this is to look at this as a somewhat old-fashioned model, but I think it can still be quite useful, which is a quadratic assignment procedure. And what QAP does is it says, I want to know whether or not a one adjacency matrix correlates with another. So for example, do I tell secrets to the people I go to dinner with? So I could imagine I've collected these different types of relationships, and I want to know whether or not there's a correlation between my secrets network and my hang out and drink beers networks. And so we can do that. We can act, and I've just used an example here, which is the Florentine Business Network. So we have two types of relations on these people. We have a marriage network and a business network, and so there's a tie on the one hand if one family married into the other family, and the second case is whether they did business together. And it turns out, of course, that these things are correlated, that in this setting, the correlation is about 0.37. Is that big or little? I don't know, it seems kind of big to me. And so we can figure out that by doing a permutation test. And the way this works, if you don't know what permutation tests are, is that once you've constructed sort of this correlation coefficient, you then reconstruct the data by randomly shuffling the rows and columns of one of the matrices. So this is another way algorithmically of saying what would happen if this association were generated only to chance, but we held constant the volume features of the network. So everyone who has out degree 8 still has out degree 8, but their association between business and marriage has been broken. So you've algorithmically taken that association and randomized it. And by the process of doing that, it allows you to generate a new correlation under this randomization assumption, under the assumption where there is known to be no relation between your two, and you can ask what kind of value you get. And so in this case, if you do that over and over and over again, I did it 500 times of a permutation test. You can say, let's randomly sort the network, take the correlation. On average, you get a correlation pretty close to 0. In that case, it's what you might expect from other sides. But the distribution of that over the sampling set is going to depend on the structure of the data. And so in this case, you can see that our observed 0.37 is far outside the bounds of what you would expect by random chances alone. So that's the way of doing this. And so this is a standard way of testing whether or not a network affects similarity of behavior in dyadic models. And so if I want to say whether or not Craig and I both smoke, or we both think that Trump is a jerk or whatever, so we have a whole series of different things that are related to us as a function of whether we've written a book together or not, right? Because that's a very big process in the political polarization world, is whether or not authors agree with each other. And so we could test that. That's my test to see if you're really asleep or not, is even my bad jokes are ignored. Then I know. If I'm not even getting a groan, then I know that you really are asleep. But anyway, you can test these models, and it's a nice way to do it in terms of similarity and to get at it without a lot of the assumptions of a standard linear model or the standard regression style linear model. It makes different assumptions. It makes assumptions that this random breaking of the permutation set is a reasonable null that is happening. And you can make good arguments for why that's not the case. There's been a lot of ink spilled on how to do these models well. In my opinion, UCINet, which is an old-fashioned desktop specialized program, is still one of the best collections of tools for doing this kind of models. So if you're interested in thinking about that, I encourage you to go find some of their tools and have a look at it. That said, the one tool to rule them all, we have built a multiple relation QAP tool into IdeaNet, and so that model is in there. The nice thing about it, Gabe, I know that I bugged Gabe last night to prep a demo of it, and now I'm going to take too much time and not let him show it. So, so I apologize for that. What's that? Great. So if you want to do it on your own, it's in there. You can see it. But what's nice about it is that you can take, the tool has a series of functions that allow you to construct the data in the way it needs to be for these models to work. And that's where a bunch of the work is at in these kinds of models, because what you have to do is you have to convert your adjacency matrix or your similarity matrix into a series of dyadic data sets. And the process of doing that is kind of a pain in the ass. And then you have to specify whether or not it's a difference or an absolute value of a difference or a matching. Or so there's all kinds of things you have to do to get these things to align right, which is no different than you have to do in any kind of data prep. But we've done a lot of that for you, and that's the advantage of it. And so it's built into the model set. All right. Questions, thoughts, comments, concerns? I know that was fast. I know it was at probably too high a level, and I can see you're sleeping, so that's why I'm going to stop.